that direction is not north, but let's pretend that it is. Now, if I'm driving north, but I'm driving around a curve that curves around that way, then a few seconds later, my direction will have changed. Instead of going in this direction, I'll be going maybe in this direction. And I can, of course, see that if I look at a distant hill or a distant object, building, I can see that now I'm heading toward it, and now I'm heading a little bit to the left of it. Now, if we assume this to be north, the problem asks us to assume that we're moving at 30 meters per second, which is about 70 miles an hour. And 5 seconds later, okay, so we're moving directly north. Okay. 5 seconds later, we're moving 14 degrees west of north. Now, this problem is posed, and I was a little bit surprised to learn that most of my class, and I'm talking about 80% of the people present, didn't understand what 14 or 12 degrees west of north meant. So, this is what it means. There's north, and we're turning toward the west. If I turn all the way around here, I'll be going west. Now, I would have to turn 90 degrees to the west to be going directly west. If I only turn 12 degrees to the west, then I'm going this way. So, you're asked to sketch a circle representing motion around a circle and put a coordinate system on it. And I'd put north going up, east going this way, because that's the way maps are usually drawn. Then you want to indicate the point on the circle where I'm traveling north. Now, this orientation has nothing to do with the orientation of the graph. Now, here's north, so you want to find the point on the circle where I'm traveling to the north. And then a point representing 5 seconds later when I'm moving 12 degrees to the west of north. Now, you should do that if you haven't already, but here's a picture. Okay, so here's the point at which I'm moving north. I'm going around the circle this way, so there's a point at which I'm moving north. Now, if you assumed I was going around the circle in this direction, then you would conclude that this is the point at which we're traveling north. And unfortunately, it wouldn't make any sense to be traveling 12 degrees to the west of north 5 seconds after you're here. So the only way the problem actually makes sense is if you are going around the circle in this direction, so that you're turning gradually to the west of north, so that your velocity vector would look like this at your initial instant when you're traveling north, and then like this when you're 12 degrees to the west of north. Now, you're going to have traveled some distance here, and in fact, in order to turn this vector 12 degrees, you're going to have to go through 12 degrees of arc. So we have a 12-degree angle here, and we have a 12-degree angle between these two vectors. Now, my perception of my velocity is that I'm going this way, and then I'm going this way. So if I was to draw the velocity vectors from my point of view, I'd draw them like this, because I'm aware that I'm moving around the circle, but I don't know how far. Again, my perception from where I'm sitting, this velocity vector goes from where I am, and this velocity vector goes from where I am, and the fact that I've moved isn't really part of my perception of the velocity vectors. Now, it's part of our perception of the overall picture, but sitting in my car, this is the way I perceive my two velocity vectors. So I'm going this way, and then a little bit later, I'm going this way. Now, I haven't changed speed because the premise of the problem is that I'm continuing moving at 30 meters per second, but I've changed direction. Now, the question then is, with that picture, with the velocity vector here and the velocity vector here, we draw two vectors, one vector to indicate the velocity when we're going north, the other vector when we're 12 degrees west of north, and that's a lot more than 12 degrees, but you get the idea. What's the change in my velocity? What vector represents the change in my velocity? Okay, well, if we add the change in velocity to our initial velocity, we should get our final velocity. What vector would I add to the initial velocity in order to get the final velocity? Well, there it is. There's our delta v vector. That's our change in velocity. Now, let's think about the angle the change in velocity vector makes with our initial velocity or with our final velocity. Initial velocity and final velocity have equal magnitudes, meaning that these two vectors have equal lengths, meaning that they form an isosceles triangle with an apex angle of 12 degrees, because the angle between these vectors is going to be the 12 degrees that we've moved toward the west. So with an apex angle of 12 degrees and equal sides means we have equal angles up here. Stop and think. What is each of these angles? Don't read the solution. Think it through first. Okay, well, two angles add up to 180 degrees. All three angles add up to 180 degrees. So these two plus this one make 180 degrees. So these two are going to be what? 180 degrees minus this. So the angles add up to 180 degrees minus 12 degrees. So each angle is 180 degrees minus 12 degrees over 2. That comes out 84 degrees. And it occurs to me right now there's a better way I could write that. So let me go off camera a second and write it down the way I'd like to see it. Okay, I've simply written out more steps of this calculation. There's a reason for that. I divide each of these numbers by 2. Or distribute my multiplication by 1/2, or my division if you prefer, through the subtraction, and I get 180 degrees over 2 minus 12 degrees over 2. That's 90 degrees minus 12 degrees over 2. That tells us what to do with this 12 degrees to determine each of these angles. And of course we divide the 12 degrees by 2 and subtract from 90 degrees, we get 84 degrees. Now, if this angle was 1.2 degrees, what would these angles be? You should figure that out. I'm going to write it down off camera. Okay, hopefully you figure that out. The same calculation scheme, the same picture would work. We just make this 1.2 degrees. Maybe we exaggerate the angle a little bit because that would be a really thin triangle. So maybe we use the same figure and just put a decimal in there and say, yeah, I know that's way too fat for 1.2 degrees, but it still represents what we need to do. So if we have 1.2 degrees and go through this whole process, what are we going to get? Well, just like we got 90 degrees minus 12 degrees over 2, we're going to get 90 degrees minus 1.2 degrees over 2, or 89.4 degrees. Now, what's going to happen if we keep letting the angle shrink down towards 0? The limiting value is the angle shrinks to 0. What's the limiting value of these angles up here if the angle shrinks down to 0? Think about that and see what your answer is. Okay, well, if we made this 0.12 degrees, then we would get 90 minus 0.12 degrees over 2, which is 90 degrees minus 0.06 over 2, which is 89.94 degrees. Now, what's the end result if we continue this process, continue shrinking this angle down? We're going to approach 90 degrees. We're going to have 90 degrees minus an angle that shrinks down towards 0, so we're going to end up with, approaching 90 degrees minus 0. Now, we're just approaching, we never actually get there, but we talk about the limit as this angle approaches 0, and it should be pretty clear that that angle be 90 degrees, so we can say as the apex angle, that's this angle here, approaches 0, the arrow means approaches 0, the angle of delta v with v, because that's what we're really looking at, there's our delta v, and there's our v, and that is actually, according to the picture, that's our v naught, but this will apply to any velocity. Okay, the angle of delta v with v naught approaches 90 degrees as a limit, so that the delta v in an instantaneous, I want to try not to use too much terminology from calculus, but in any given instant, the velocity is changing in a direction perpendicular to the velocity. Now, v naught is tangent to the circle, so that delta v is what? It's toward the center, because the tangent is perpendicular to the radial line toward the center. Now, I haven't written every detail of the argument, but I've written the conclusion at every instant the velocity is changing in the direction toward the center. As you move around this circle at constant velocity, your velocity is always changing. If you're moving this way, whether this be north or northwest or northeast or south, your velocity is always changing in a direction perpendicular to the velocity, in a direction toward the center.